Ever looked at a volcano like the majestic Mount Rainier and wondered what's happening deep beneath its icy surface? It's not just a simple pipe leading straight down to a pool of magma. The reality is far more complex, a hidden world of fractures, chambers, and pathways that dictate when and how this giant might awaken. Today, we re-journeying deep into the earth to uncover the secrets of Mount Rainier's volcanic plumbing and discover how the immense stress within the mountain itself shapes its eruptions. Let's start with the basics. Mount Rainier is a stratovolcano, built up layer by layer from countless past eruptions of lava, ash, and rock. Deep below, somewhere between 8 and 30 kilometers down, lies a massive magma reservoir. This isn't a bubbling cauldron like in the movies, but more of a mushy, crystal-rich zone. Think of it as a slushy, but instead of ice and syrup, it's molten rock and solid crystals. This is the source, the heart of the volcano. Now, for this magma to cause an eruption, it has to travel upwards. But how? It doesn't just melt its way through solid rock. Instead, it exploits weaknesses. The Earth's crust isn't a solid, uniform shell. It's fractured and broken. Magma is buoyant, it's less dense than the surrounding rock, so it naturally wants to rise. It forces its way into existing cracks, widening them and creating new pathways. These pathways are called dikes and sills. A dike is a vertical sheet of magma that cuts across rock layers, while a sill is a horizontal sheet that squeezes between them. Imagine injecting honey into a block of layered, brittle jello. The honey would seek out the weakest points, pushing its way up vertically and spreading out horizontally where it can. That's essentially what magma does. At Mount Rainier, scientists believe there isn't just one main conduit, but a complex network of these dikes and sills, forming a sort of arterial system for the magma. This is where internal stress comes into play. A mountain, as massive as Rainier, exerts incredible pressure on the rock beneath it. We're talking about billions of tons of rock and ice. This immense weight creates a stress field within the crust. This stress isn't uniform. It varies depending on the weight distribution, the structure of the underlying rock, and even the presence of ancient fault lines. This stress field acts like a gatekeeper for the rising magma. It can either clamp fractures shut, blocking the magma's path, or it can create zones of weakness where fractures can open more eyes. Think of it like this. If you squeeze a sponge, some pores will close up, while others might be forced to open wider. Similarly, the weight of Mount Rainier directs the flow of magma, favoring certain pathways over others. Recent studies using seismic imaging and GPS data have started to map this out. Scientists can detect tiny changes in the ground surface, measured in millimeters, which indicate that magma is moving or that pressure is building. They can also analyze the patterns of tiny earthquakes, or seismic tremors, which are caused by rock cracking as magma forces its way through. These signals help them build a 3D model of the plumbing system. What they found is fascinating. The stress from the mountain itself seems to create a stress barrier around the shallow magma storage zones. This barrier can trap magma for long periods, allowing it to cool, change its chemical composition, and build up pressure. The magma might stall out several kilometers below the surface, forming a smaller, more temporary reservoir. This is a crucial point. The type of eruption we see at the surface, whether it's a gentle lava flow or a catastrophic explosion, depends heavily on what happens to the magma during its journey. If magma rises quickly from deep down, it's hot and the gases within it are still dissolved, leading to a more effusive or flowy eruption. But if the magma gets trapped in a shallow chamber, as the stress field at Rainier seems to encourage, it starts to change. It cools down, becoming thicker and stickier, like honey left in the fridge. More importantly, gases like water vapor and carbon dioxide, which were dissolved in the magma under high pressure, start to come out of solution and form bubbles. This is exactly like opening a can of soda. The pressure release allows the dissolved CO2 to form bubbles. When enough gas bubbles form in this thick, sticky magma, the pressure can build to an explosive tipping point. The stress from the mountain's weight might hold it back for a while, but eventually, the pressure from the gas-rich magma will overcome the strength of the surrounding rock. When it finally breaks through that stress barrier, the result is a violent, explosive eruption, blasting ash and rock high into the atmosphere. So, the very thing that makes Mount Rainier so imposing, its immense size and weight, is also a key factor in controlling its eruptive behavior. The internal stress it generates creates a complex, challenging path for magma. It forces the magma to stall, to cool, and to build up explosive potential. It's a geological pressure cooker, where the lid is the mountain itself. This understanding is vital for hazard assessment. By mapping the stress field and monitoring the movement of magma, scientists can better predict where and how an eruption might occur. They can identify which flanks of the volcano are under more stress and might be more prone to failure, potentially causing landslides or directing the flow of Lahore's fast-moving mudflows of volcanic debris and melted ice, which are one of the biggest hazards at Rainier. For instance, if monitoring shows magma is moving into a region where the stress field is known to promote vertical dikes, it could signal an impending summit eruption. If it moves into an area where horizontal sills are favored, it might mean the magma is spreading out and the immediate threat is lower, though pressure might be building for a future event. It's a giant slow-motion puzzle. The pieces are seismic data, ground deformation, gas emissions, and geological mapping. And the picture they form is of a dynamic, living mountain. The pathways are not static. They change over time. Each new injection of magma can create new fractures and alter the stress field, changing the plumbing for the next eruption. Mount Rainier hasn't had a major eruption in about 500 years, but it is an active volcano. It's not a question of if it will erupt again, but when. Understanding the intricate dance between rising magma and the mountain's internal stress is one of the most important tools we have to prepare for that day. It allows us to read the subtle signs the volcano gives us and to anticipate its next move. So the next time you see that beautiful, snow-capped peak, remember the incredible complexity hidden beneath. It's a world of immense pressure, fractured rock, and rising magma, all governed by the laws of physics. Exploring these hidden pathways isn't just for scientific curiosity. It's essential for the safety of the hundreds of thousands of people who live in its shadow. Thanks for joining us on this deep dive into Mount Rainier. If you found this journey into the heart of a volcano fascinating, be sure to hit that like button and subscribe for more explorations into the science of our amazing planet. See you next time.